Welcome to Study Loop.
Okay, today we're going to be predicting molecular structure, drawing the Lewis structures of a few different compounds. So the first one we have is BRFI2. So first what I like to do is calculate all the valence electrons. So here they're all halogens, so 2, 3, 4 times 7, or we have 28 electrons to work with. Now we want to put the least electronegative atom in the middle. So if we're using our electronegativities chart, iodine would be our least electronegative. And that means we can put iodine and bromine and fluorine around it. Then we want to fill in our valence electrons. And count up how many we've used. So far, just as lone pairs, we've used 6, 12, 18. And then in the bonds, we've used 6, so that's 24 total, which means we have 4 more electrons to add in. So whenever you have electrons left over, you add them on the central atom. So right now, the way I've drawn this, we have a T-shaped geometry because this is a mimic of trigonal bipyramidal. So this is T-shaped. Another way this could be drawn would be like this. And this is again derived from trigonal bipyramidal, but it actually ends up looking like trigonal planar without considering the electron pairs. And then if we add one lone pair in an axial position, and one in the equatorial position, this ends up looking like trigonal pyramidal. Now, if you're looking at problem 111, this is the one example that we do see there on those variations, but these other two would be possible. Probably not as likely though. Okay, the next structure we have is XeO2F2. So we have 8 plus 12 plus 14 electrons to work with. So in total, that's 34. So xenon here is the least electronegative because it's a noble gas, so it's going to go in the middle. And then we're going to put oxygen and fluorine around it. From my experience, oxygen typically requires 2 bonds. So I'm just going to go ahead and add in double bonds here because I know the formal charge of oxygen will be satisfied if I do that. And then I'm going to go ahead and add in my lone pairs, and then I'm going to count to make sure I didn't use too many electrons. So far in lone pairs, I've used 6, 12, 13, 14, 15, 16, 17, 18, 19, 20. And then in my bonds, I've used 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, which means I have 2 electrons left over and they go on the central atom. Alright, so the way I've drawn this right now, it's a little funky. But again, we have 5 things around our central atom, so this is still going to be derived from the trigonal bipyramidal. So the main one we could draw, and I'm just going to have to redraw it here, is the seesaw structure, and you can see that in problem 111 again. If I put the electron in the axial position, you end up with something that looks more like this. And it's not really tetrahedral. It's almost like a half pyramid, which doesn't really, we don't really see this one as often, but it could be possible. But in this case, with the one lone pair, seesaw is probably going to be the most likely. All right, and then lastly, we have TeF2Cl3 minus. Which means we have 6, 14, and 21, plus that 1 electron from the negative charge. So we have 35, 42 electrons to work with. All right, so here tellurium is our least electronegative, and we're going to put everything around it and can count up all of the electrons that we've used. So this one, all of them have 6, so 6 times 5 is 30 that we've used, plus 10 in the bond, so we've used 40 so far, which means that we have 2 left over. And we put those on the central atom. So now this one has 6 things around it, so it's going to be derived from octahedral structure. And if we put it in the axial position, we get this square pyramid structure. And that's pretty much the only one that you typically see with one lone pair in an octahedral derived one. You could come up with another unnamed one like we did up here, but that's not necessary in this particular case. And so that is how you determine the structure of these different compounds and predict their different geometries based on whether you put the lone pairs in axial positions or equatorial positions.